Proof of de Moivre's theorem. Well, let's start with let z equal cos theta plus I sine theta. And we're going to look at differentiating a complex number. But let's first of all look at vectors. Now you must remember vectors from M2. And you had a position vector r is cos theta in your I direction plus sine theta in your j direction. And then when we differentiated r, which we called r dot, or dr d theta, remember we differentiate the I part, so we get cos becomes minus sine theta in your I direction, plus, and then we differentiate sine, which is cos, in your j direction. So we write that as sine becomes cos theta in your j direction. So we don't differentiate the vector, we just differentiate the thing in front of the vector. Now we're going to do the same thing with complex numbers. So we've got a real part, which is similar to your I direction in a sense, and your imaginary part, which is similar to your j vector. So let's go back and do that. So we're going to differentiate. So we've got dz d theta. And dz d theta is differentiate the real part, which becomes minus sine theta. Differentiate the imaginary part, which is cos theta. So that would be in your I, would be cos theta. Now, we also know that iz from above is equal to I cos theta minus, because I squared would be minus 1, minus sine theta. And if you notice, this is exactly the same as what we get for dz d theta. So we've got dz d theta is equal to I times by z. Now let's go on to a new slide here. So we've got dz d theta is equal to I z. Now we've got C4 differentiation here, or C4 integration rather, when we'd use our method of separating variables. So I'm going to take everything with z and dz onto one side and everything with d theta onto the other side. And I'm just going to separate my I bits, looking at my real part and my imaginary part. So I'm going to write my integral sign, so that will be 1 over z, taking the z to the left-hand side, dz, and that will be equal to, now my I component would be the integral of 1 d theta, because I've taken the d theta over to the right-hand side. Now we just do our standard integration here, so the left-hand side becomes ln z is equal to, well, my I component is integrate 1 with respect to theta, and we get theta. So I'm then going to undo the logs, so that gives me e to the I theta is equal to z. So there we've proved that a complex number, z, which is of the form cos theta plus I sine theta, must be equal to the exponential form e to the I theta. So e to the I theta is equal to z. So let's take the nth power of both sides. So e to the I n theta is equal to z to the n, which I should have written e to the I theta to the power n. But using our rules for powers, we've got e to the I n theta. Now from our laws of, or from the previous page rather, where we've got e to the I theta must be equal to cos theta plus I sine theta. Now if that's the case, then if we've got our angle n theta, that must be equal to cos n theta plus I sine n theta. And we also know that z to the power n is cos theta plus I sine theta to the power n. So therefore, we've got cos theta plus I sine theta to the power n must be equal to cos n theta plus I sine n theta. And there we have de Moivre's theorem.